enough about aggregating impacts over time. We're going to aggregate impacts over people now. Returning to the general theme, you do not care about the distant future, faraway lands, or remote probabilities. You do not need to care much about climate change. And the turn is now for the faraway lands. The impacts of climate change differ greatly between countries. We spent quite a bit of time on this, particularly in this graph. It shows the impact of a 2.5 degrees global warming on the 200 or so countries in the world who are here ranked by their per capita income. And you see this very clear relationship that poorer countries are more vulnerable to climate change than are richer countries, and richer countries may even see benefits. The question then, of course, becomes, how do we add these numbers up? And what people did at first was that they estimated these impacts for every country or region in the world, and then just added up the dollar numbers. That was done in the context of the second assessment report of the Intergovernmental Panel on Climate Change, which is the United Nations organization, and this caused a furore. This was a enormous row at the time, and the reason for that is that if you monetize these impacts, one of the impacts that you monetize, that you put a dollar value on, is the impact of climate change on human health. And you would use the observed values for this. And the value of statistical life, the willingness to pay of people to reduce the chance of premature mortality, is a willingness to pay, and willingness to pay always reflects ability to pay, and therefore these numbers vary very greatly between countries. And essentially, if you then just add up these dollar numbers, then what you say is that we value the impacts of climate change on the UK, and the value of statistical life in the UK is £7 or £8 million, and we value the impacts of climate change on India, and the value of statistical life in India is, what is it? Would be perhaps £300,000, and that's how we value those impacts, and we add them up. And essentially what you've done then said is, let's make it 6,300,000, that we care 20 times as much about somebody in the UK dying than somebody in India dying. And it's not wise to say that in the United Nations context. There is no straightforward way out. Some people have said, well, you should just value these lives equally across the globe, but you cannot mess with these numbers, because the value of statistical life is a measured thing. It's how much people are willing to pay based on wage data and those sort of things, expenditures on healthcare, expenditures on safety. It's an empirical quantity. You cannot just change the data. And there is an issue again with internal consistency. You cannot say, as some people have said, well, for a global problem like climate change, we should use the global average value of statistical life, and for a local problem we should use a local value of statistical life. Then you create large inconsistencies in your public policy advice. Going back to the example of road safety, which is a local problem. So if the UK government makes decisions about road safety, then it should take the local, the UK value of statistical life, which is say 6 million, But if it invests in greenhouse gas emission reduction, that's a global problem, and therefore it should use the global average, and let's make that 1 million. So that immediately implies that the UK government should spend much more money towards road safety than towards greenhouse gas emission reduction. And vice versa, the government of India, if it invests in road safety, which is a local problem, then every life saved is worth £300,000, but if it invests in greenhouse gas emission reduction, then every life saved is worth £1 million, the global average, and therefore the government of India should invest much more money in greenhouse gas emission reduction. And that seems to be a peculiar conclusion, even if you accept that life saved is a life saved. So why would I count a life saved through road safety more or less than a life saved through greenhouse gas emission reduction? So just messing with these values cannot be the answer. Instead, what you can do, and perhaps should do, is use so-called equity weighing. And equity weighing works as follows, and here we follow the procedure suggested by Sam Venkhauser and David Pearce and myself. Is that you use these things called equity weights. So what we're interested in is DW, that is the monetized impact for the world, right? And what we have are the DCs, the monetized impacts for every country C. And the question then is, what do we do? How do we get from one to the next? Well, in an abstract way, what you should do first is say, well, we have these dollar values for different countries, but we cannot just add them up, because a dollar to a poor woman is not the same as a dollar to a rich woman. So really we would want to express these impacts in utility rather than in dollars. So what we need to do is multiply this with U sub C, which is the first partial derivative of utility to consumption. And then we essentially measure things in utils rather than in dollars. So that is the first transformation then that we need to apply. Then the second transformation, the W sub U, is how much does the utility of a particular country, or the average utility in a particular country, contribute to global welfare. And that's the first partial derivative of the welfare function, the global social welfare function, to the utility in a particular country C. And then you have a problem, because we want these numbers in dollars. We want to express this as a carbon tax, so in dollars per ton of carbon, for instance. But we now have expressed everything in welfare units. So we need to transform things back to money. And one way of doing that is to divide by the W sub M, which is a slightly abstract term. Essentially what you do there is you ask the question, what if the global budget constraint is slightly slackened? What if a Martian would come along and give us $1 additional? How much would global welfare improve? And that then, because you slightly slacken the budget constraint and you measure it in welfare terms, that is a unit, the unit of that thing is global welfare by dollars. So then you're back in dollars again. So that is one way of transforming everything back to dollar terms. Now this all sounds horribly abstract. If you assume that the utility function is CRRA, constant relative rate of risk aversion, and you assume that global welfare is the sum of national utilities, not weighted or anything, just summed up, then this ugly term that you see in the middle there transforms into a much simpler and much more intuitive term, yw over yc raised to the power eta, where yc is the average per capita income in country C, yw is the average per capita income in the world, and the eta is the rate of risk aversion, the curvature of the utility. Again, it's actually not the rate of risk aversion. In this case, it's the rate of inequity aversion. So how does this term works? Well, your eta is positive. So if you're in a country where the national average income is lower than the global average income, then you divide a big number by a small number, so you have a number that is greater than 1, then you raise it to a positive power, so you still have a number that is greater than 1, and that means that in poorer countries, in countries where the income is below the world average income, you attach a greater weight to those impacts, and vice versa. If you take a richer country where the national average income is above the global average income, then yc is greater than yw, and that number is smaller than 1, and you raise it to a positive power and it stays smaller than 1, and that means that monetary impacts in richer countries receive a lower weight. So that is what equity weights do. You essentially pay more attention to the plight of the poor. There's an alternative way of justifying this or thinking about this, and that is to return to health impacts, and that is of course where the story started. The story started. So we have that the W is a weighted sum of our national impacts dc. Those national impacts d sub c we can express as the total number of deaths, I in country C times the value attached to those deaths, and that's the national value vc. And then we can say, well, let's assume that that national value vc has an income elasticity epsilon. That is, it scales up and down depending on our income elasticity with per capita income. And then we can rewrite that VC as some sort of anchor value. Let's take the global average, VW times the difference in income, the ratio of incomes rather, it's the relative difference in income, YC over YW raised to the power of the income elasticity. And we're still on the same terms. Now if we then make the assumption that the income elasticity of health valuation is equal to our rate of inequity aversion, so epsilon is equal to eta, then YW cancels against YW and YC cancels against YC, and what we have is that our total global damage is the national death toll, YC, times the global average value of a statistical line. Now, there is no reason whatsoever to assume that the income elasticity of health risks, the valuation of health risks, is equal to the rate of inequity aversion. There is a relationship between the two parameters, but there's absolutely no reason to assume that they are equal. But if it so happens that they are equal, essentially what equity weighing does is value all impacts at their global average. And way of interpreting this. Does this matter? Yes, it does. You've seen the graph to the left before. That shows the relationship between the social cost of carbon, the pure rate of time preference in the different colors, and the curvature of the utility function, labeled rate of risk aversion. And that's to the left. And to the right, we're looking at the same relationships, but now with equity weighing added to the picture. Some things stay the same. So the relative position of the three curves is the same. So the green curve lies above the blue curve, lies above the red curve or the brown curve. That is to say that the lower your pure rate of time preference, the greater the carbon tax you would want to impose. So that hasn't changed. Also in the green curve, what you see is that at least initially, the greater the rate of risk aversion, the harder you discount the future, the lower the social cost of carbon. Now, if you compare the two graphs, then what you see, if you focus, for instance, at what happens at a rate of risk aversion of 1, then in the left graph you're at almost 0. The vertical scale is the same on the two pictures. But then if you look at the right graph at a rate of risk aversion of 1, you see actually that the social cost of carbon in the green line is substantially higher. It's still very much different from 0. That is to say, equity weighing, because most of the impacts fall on the poor, actually increases your concern about climate change. This is not the end of the story. I'm going to blow up the figure in a sec, but there's also one thing you should notice, and that is at a 0 curvature of the utility function, the numbers are unchanged. And that of course follows from the equity weights. If your epsilon is 0, no, it's an eta. If your eta is 0, then of course your equity weights are always equal to 1. Every country gets the same weight, and therefore at that particular point numbers do not change. So now let's blow up the figure and see what else is going on. So if you focus on the green curve again, then what you see is that as the utility function becomes more curved, you discount the future harder, and therefore the social cost of carbon falls. But not as fast as in the previous one, right? I just talked about it. Now what you see is that if the utility function becomes more curved, you see that the social cost of carbon is going up again. So now why is that? That's because the curvature of the utility function now fulfills a double role. On the one hand, it governs the trade-off between your poor self today and your richer self tomorrow, but it also covers the trade-off between rich people and poor people. And what you see is that for a modest curvature of the utility function, a modest rate of risk aversion, the discounting effect dominates. That the higher this number, the more you discount the future, and therefore the less you care about climate change. But then for very high numbers, the other effect starts to dominate, that the higher this number, the greater emphasis you place on the plight of the poor. And what you see is that the social cost of carbon goes up again, and the relationship between the curvature of the utility function and the social cost of carbon becomes ambiguous. It can go up, it can go down if you increase the curvature. So that is the green line. In the blue and the brown line you see something that might surprise you, and that is the social cost of carbon becomes negative. It's not a PQ tax, it's a subsidy. You should increase the rate of greenhouse gas emissions So now why is this? This is for a high rate of inequity aversion, but also for a high rate of risk aversion and for a relatively high pure rate of time preference. So essentially what we are really interested in is what happens in the short run. We use a high discount rate, and what happens to the poor. We use a high rate of inequity aversion. What does climate change do to the poor in the short run? Well, it's not so much climate change that does it, but it is the CO2 emissions that do it. CO2 emissions cause climate change, but CO2 emissions are also, or CO2 concentration, CO2 in the atmosphere is also plant food. We talked about that when we talked about the impacts of climate change. More CO2 in the atmosphere makes plants grow faster, but it also makes plants more water efficient. So this is particularly good for countries in semi-arid areas that rely a lot on agriculture. That is, countries of the Sahel, northern India, and those sort of places would actually see a great benefit of CO2 fertilization in the short run. But if you use a high discount rate, we're only interested in the short run, and that means that more CO2 in the atmosphere is actually a good thing. And therefore, if the only thing we're interested in is what happens to the short run and to the poor, then we should pump more CO2 into the atmosphere, and that is why these numbers become negative, and we should subsidize greenhouse gas emissions.